Welcome everyone to this dialogue section under Masterminds Masterclasses. My name is Sean Hon, an assistant professor of Department of Mathematics of Hong Kong Baptist University. Today is my great honor to introduce Professor Mok Ai Ming from University of Hong Kong. Professor Mok is Edmund M. Pekizek Professor in Mathematics, Director of Institute of Mathematical Research, and Chair Professor of Department of Mathematics. He has also held several important positions, including member of Academy of Sciences of Hong Kong and many more. Based on his outstanding research achievement, Professor Mok has received numerous prestigious awards and honors from various international committees and organizations from all around the world. The list of his honor really goes on forever, so I'm just going to be brief. Before we start officially, may I remind everyone today's theme of this dialogue section, which is to provide a platform for our young scientists to learn and get inspired by world-leading scientists, by their research journey and personal experience. Each of us here have different background, right? We have postgraduate students, we have undergraduate students, and a newbie in academia like myself. So we all have our different worries and concerns and questions to ask. So without further ado, I'd like to welcome Professor Mok. So maybe it's going to be casual, right? So maybe each of us can take turn, ask a question. We can start with Vilina, maybe.
I would like to ask Professor Mok, when and how did you determine your specialties and your field?
Determine my specialty. Okay.
Yeah.
So I guess, well, first of all, I chose mathematics very early. Well, as soon as I get into undergraduate, I had some idea in which direction I would try to work on. So for me, it's pretty straightforward. Yeah. But the reason why I could determine my specialty, so to speak, is that I read a lot when I was in high school. So I spent a lot of my spare time reading. So at that time, you don't have the internet, and I didn't have access to university facilities. So it was essentially from my high school and also from the commercial world. So, but I managed to, because I was very interested, I managed to read quite a bit in advance. So by the time I left Hong Kong, I essentially have the, should I say, the undergraduate level mathematics is essentially, I'm essentially comfortable with it. Should I put it this way? So then I had the luxury of trying to choose a direction to research on, to work on. So I was fascinated by complex numbers, so I worked on complex geometry. I will, in the seminar later on today, say something about that direction.
It's amazing. I guess a quick follow-up question is, I mean, out of many branches in pure mathematics, certainly there are a lot of different research directions, even in complex numbers, right? Why are you so attracted to your current profession right now?
Yeah, so let me put it this way. It has to start from very early. It's not just what I do eventually, but why I was interested in mathematics in the first place. Mm-hmm. So I guess I am a product of the education system in Hong Kong. Yeah, at the time when things are pretty, how should I put it, pretty straightforward, quite competitive. At that time, we had to take public exams, even at the age, well, as a sixth grader. So after primary school, you have to take an exam.
Oh.
And you're only asked to study essentially for the exam 3 subjects, Chinese, English, and mathematics. So the role of mathematics, right from the very beginning, an essential part, is multiple choice, and you have to be doing things fast and so on. So I was a good student. Okay. So and mathematics was one of my favorite subjects, but I should also say that I was interested in all, right? So then I like, well, of course you did some very simple things like the quick calculations and so on and so forth, and it interested me to find solutions fast. Now, then I moved to high school, and I happened to be in high school with a lot of essentially good resources in the library. So I was at St. Paul's Co-ed, and I spent quite a bit of my time reading in the library. So I managed to be quite to define for myself quite early a scope of mathematics. So I wouldn't say that I will do complex numbers right from the very beginning. But mathematics for me was one. You can say ideally that a mathematician is a truth seeker. So before you know which direction is the most important, you would try to learn everything. But of course, you can only learn things to different degrees of depth, right? So I learned what was accessible to me. So I learned calculus quite early. And then when you see the complex numbers was some like God-given miracle that you can do certain integrals with the exponential function, e to the power ix.
Oh yeah, like the Euler's.
Yeah. So then right away, it didn't take me any time to accept that there's a number of squares equal to -1, right? So from the logical point of view, so everything that you introduce is just part of a new structure. All you need is consistency. Right? So then this usefulness this importance for me was quite early. And then, so in high school, and I went to the city hall also. So there's a good library in the city hall. And I read books in algebra, like Serge Lang's book on algebra. I like that type of book, which introduces you to a big subject quickly without going too much into nitty-gritty details. And then I read one of his books. This is a book on transcendental numbers. And the simple question, like for instance, is pi a rational number? This is already a very difficult question. And this is a field that fascinated me. But I knew that it was a very difficult subject. So I kept interest in such a subject, but I kind of learned things that are in some sense methodologically related. So it happened so many years afterwards that I did something in a certain analogous way related to such questions. So somehow my early reading has inspired in me a certain search for contribution to some classical questions. Okay, and as I read along, so I read Cauchy, Weierstrass, and so on and so forth, and I realized the importance of complex analytic functions. Then I went into several variables. There was a newer object and subject, and was sort of something like a century old by now. But then it was very important subject. It has different lengths to different subjects within, should I say, fields within mathematics. So that's why I have chosen quite early, well, first of all, to do complex analysis and then to do several complex variables, which is still, in a certain sense, it's calculus, but in the complex domain, and then in several variables, knowing that several variables are different from one variable. It's not like in real calculus that when you do two variables, of course, you have more dimensions, but then the concepts are unified. Whereas in a complex analysis, when you introduce an extra variable, it's a different world. So then I went into several complex variables. Yeah.
Professor Mo, you mentioned that you were fascinated by the formula I square equals -1, and so am I. And I think, the complex, the complex numbers is a very fascinating system. I'm just wondering, could you give me some ideas? Can we find some, projections on our real life or the universe? Can we find some complex structures? For example, the complex number I, we can understand it as rotation by...
Yeah, so you are looking at it geometrically. You want to look at it. Of course, for me, I is an algebraic object. You just define a structure in which there's a certain object whose square is equal to -1. And then you try to work out from the basics and get consistent theory. In real life, of course, one of the earliest attempts, one of the reasons why I was introduced was that you try to solve equations, right? So from the quadratic formula, you may think that it's artificial. I just introduced square root -1, I just call it by the name of I. But then there are real life questions, like for instance, you take a cubic equation, right? And it's increasing. So it crosses from -infinity to infinity, and it must cross the x-axis, and therefore it must have a certain root. So this is a real-life problem. You really want to find this root, whatever the meaning, the physical meaning of the function and so on. So it turned out that Well, one can find formulas for the cubic and quartic equations. And this equation involves I. Although in the final analysis, you're solving something which is real. And you get expressions involving the I, and somehow in the final outcome, for one of the roots, they cancel each other, and then you get a real number. So in a certain sense, at least practically, it gives a justification for those skeptical of the introduction of this, so to speak, artificial number. But from the point of view of mathematician, I would look at it more structurally. So you introduce structures, there are certain structures you can see, you visualize the real world, three-dimensional world. Or maybe you extend it to four-dimensional, whatever. But for the mathematician, depends on your point of view, I'm more a structuralist. I look at things with structure. And as long as the structure is consistent, I can use it.
So, Professor Mark, you mentioned that you love mathematics, you're passionate for it when you were an undergraduate student. So, was there ever a critical moment where you decided that, doing research is really something that you want to do for the rest of your life?
I think I was there a little earlier. Certainly, I was interested in mathematics as a primary school student.
Oh, okay.
And then I decided more or less to do mathematics when I was in high school. And then, of course, I had lots of interests. So I have to make some choices.
Yeah.
So because I'm interested in literature, I'm interested in linguistics and so on. And it turned out that some certain things that I learned could be useful for me later on in my own career. So I guess it's very important that one develops one's interests. And how you put your talents, how you put your interests together to constitute your life is a long process. And in my case, the choice of mathematics was easy. So I guess, well, of course, it has something to do with the training. And also, I think I learned it like a game. So when you're in primary school, being able to calculate very fast. I'm not saying that this is a must. I think that one must do. But being able to do it faster is certainly something that's rewarding in some sense. But then you learn, you think further and you learn further. You don't just calculate fast, but you calculate with the knowledge of why you can do it faster. Then you look into structure. Then the world is structural for me. So I look at everything as trying to understand structure behind things. If I had the second life, I might or might not have chosen mathematics. But whatever, I look at it as a science in the wide sense of the word. So in the German, science is called Wissenschaft. It's the art of learning, so to speak, of knowledge. So anything that's systematic, that can constitute knowledge is something that could interest me. Of course, I have to make some choices. Yeah. But then in my case, my interest was already there when I was very young. And then I got more and more interested when I was able to, in some sense, have dialogues with the peers who are interested also in mathematics. And also, well, maybe from my teachers also. Yeah. So I was lucky to have had a teacher who was very clever in trying to arrange the curriculum. This has some certain historical dimension. This was at a time when there was introduction of so-called modern mathematics, or new mathematics. As a matter of fact, it was just the sort of repeating what has been done in the West, trying to introduce set theoretical notations and logic and so on. So at that point, in the standard textbooks, one tries to water down the content of the mathematics. Things look very formal, very symbolic. But I had a teacher who was clever enough to integrate old mathematics into new mathematics. And thereby, of course, we still learn the Euclidean geometry like in the so-called old mathematics. But because of the new formalism, we learn probability theory, matrix, linear algebra, earlier than others. So that was one reason why I was more prepared than others. Of course, this applies to anybody who was in my class. But then I learned something further on my own because of my interest. But I must say that a good teacher is extremely important. She made it so natural for me to learn new things. And I didn't learn less because there was a reform. I learned more because there was a reform. So then I guess that was in high school. So by the time of high school, this goes beyond just doing quick calculation. Where quick calculation could be rewarding, but this is just fun. But then knowing structural things is much more important, and that happened in high school.
So having a great teacher is crucial. That's why we're having this master class right now, right? By the way, funny fact, students nowadays, they only start to learn linear algebra in year 2. So certainly, yeah, at least that's true in Baptist University. So anyway, my point is, certainly having a good mentor does matter. We always want to, get prepared as early as possible.
We had our own textbook.
Oh.
And the textbook, I don't know whether other schools are using it, but one interesting thing. So I am not from I was not from a well-off family. So in order to pursue my interests, I need to be financially independent. So I was a mentor or a private teacher, a private tutor. Quite early in my life, I was in grade 8. I was already a tutor. So I earned my money so that I can buy books. I even at one point tutored somebody at the same level as mine. And I used the textbook from my high school to teach her. So I don't think the textbook was used elsewhere. I think it was used only in my high school, but it contains more information. And I can choose within the textbook things that are new to my students.
Can I borrow it and teach my students? It's just amazing, really. Oh, maybe we should move on to the next question.
Yeah, hello everyone. I'm Lee Ka Hong, Howard, and I'm a year 4 undergraduate student in HKUST. And I've heard that there is a saying that in math research, you must know 2 out of 3 areas, like in analysis, algebra, and geometry. These 3 areas that actually have some connections, and I want to know when you face like some difficulties in research, will you like to learn broader or like go deeper into one area?
Well, let me put it this way. As a career mathematician, of course, I try to learn everything. But of course, when you actually do research, you work on something specific. Right? There's a certain roadmap. If I map out my personal experience, I started to do analysis, then I moved into geometry, then I got interested so I did differential geometry. Then I got interested in algebraic geometry, and I used complex analytic method to study algebraic geometry. And then recently I moved into something that has some overlap with number theory. So in a certain sense, I was able to do this chain of research because I had a broader background. So should I acquire this broader background when I was a student, or should I do my research and then put all my efforts into my research? So I guess you do this at different parts of your career or different parts of your study. So I would say that for me, mathematics is one. I'm talking more about pure mathematics. Of course, in applied mathematics, you apply a theory that has been developed, but then there are other criteria like its applicability, which is not the point of discussion of what I'm saying now. I'm just trying to say that in order to do mathematics that has a certain meaning or broader meaning, you should keep your eyes open to different areas of research. But whereas in actually doing research, of course, you have to get very deep into it. So you have to be able to manage tools of research. So there's a tendency, because nowadays things are more accessible. You have the internet, you can have YouTube lectures. So of course, one gets attracted, and maybe one then gets more familiar with various new terms more easily, but it's not clear that whether you understand it. I feel that if you really understand something, then you can produce new research. So understanding has different levels. So in order to do good research work, one has to really understand it. And what the word really means is something that you have to manage to understand. It means to depth, to some depth, and you have to understand what other people don't understand. So to answer your question, I think at different stages of your career might be different, but it's advisable that you have a broad background. And then you also get very deep into a certain direction when you actually do research. Yeah. I would not have imagined that certain things that I learned could be useful to fields that I'm working in, for instance. So it was good that I chose that approach. Yeah.
Speaking of doing research, how do you find research problems? I mean, how do you find problems that you think are worth working on?
Okay, all right. Of course, then one has to have a good environment. Okay, so if you are with peers and with teachers who are at the frontier of the subject, of course, then you get to know these subjects. But even at the time when I was a student, when the information was not so widely distributed, there were still textbooks, there were still proceedings of meetings and so on. So even if I could be a little late with the information, I could still get information with some delay. Now, in pure mathematics, there are many well-known problems. These are known either as a problem or an open problem or as a conjecture. So already in my thesis, I worked on something which was a conjecture, so that was well known. So then I guess mathematics is a subject in which certain problems stay unsolved for a long time, so it has stayed there. The fact that it has stayed there for a long time means that it has a certain difficulty, but also it gives you the challenge and also perhaps the motivation of trying to attack it. So in a way, I was not afraid to do hard mathematics. Because you could be disappointed every now and then, but the success or the joy of success after a long try still is worth all the efforts. So in my case, I'm aware of the problems. I was aware of the problem from my vicinity, from the literature, and from the fact that certain problems were historical. Yeah. So if you talk about number theory, many of the problems have been there for centuries. Of course, then you have a question, well, should I try this very difficult problem? Then, of course, there's a practical side. My advice is that you should do what you can do. But at the same time, keep abreast of the development and try to dream about possibilities in the future. A dream can eventually turn into reality when you have thought about it thoroughly, and you have to have something to build upon a theory, and this is your knowledge base, and your knowledge base must grow, otherwise you will be stagnant. Yeah. So you try to do research on very pointedly at one problem or at a number of problems, but while keeping at the same time your eyes open for new directions. Yeah, that's my advice.
So one mustn't forget about the practical side of doing research, because as researchers, we have to get grants and we may have to think about the impact, right? So my question is, how do you balance the pursuit in mathematics or the truth versus, the practical consideration?
Yeah. So I understand your question. So from my point of view, whether something has an impact is also up to you to formulate. And if you have a perspective that is convincing to yourself, then you should try to articulate it. So one shouldn't give up on a problem only because it was not as well known. Maybe you can make it well known. Of course, then yes, this doesn't have a history yet, and I am not sure that it's accepted by the mathematical public right away. Then you have to judge. If it's, you should always have a number of problems in mind, and this is the purpose for getting a grant. So everything, this is a social contract. In a social contract, there are constraints. Like everything, there's a constraint. So you try to choose the one that would optimize your chance. I think that's fair. But it's something that you are interested in. You don't do research because you want to get a grant. You want to get a grant to do the research that you want to do. Right? So you should always think in this direction. So in a practical point of view, I think one should always have more than one line of research. So that's why whatever whether it's physics or mathematics, and in mathematics, whether it's applied or pure, you should have more than one major line of research in line so that you can alternate. So, because things take time to develop. If you write grant after grant on the same theme, you exhaust your own talents on the subject. My advice is that you should always have a few lines of research accessible to you and in which you want to do research. And then, of course, you cannot map out the future, but you can certainly try to have a flowchart on how to deal with the number of problems you're interested in, and the reality or the practical issues of whether some will be accepted by the mathematical public. So I guess that's my advice.
Thanks a lot. That's a good advice. That's
So speaking of multiple research ideas, I have a question, Professor Mo. So is it common for you to work in multiple research projects at the same time? And how do you handle them properly?
So I work in different subjects. As a matter of fact, I was first trained as an analyst, then I do differential geometry, and because I work on complex numbers or complex value functions, I was, so to speak, a complex differential geometer. Then I realized that I can make use of complex differential geometry to work on problems in algebraic geometry and ideas, and you translate the ideas into that. And so there's some kind of cross-fertilization. This you might call interdisciplinary. It's all mathematics, but in different identifiable branches of mathematics. And then it turned out that that idea into algebraic geometry has repercussions also in the problems in number theory. So then I move on to number theory. I almost always have a couple of lines of research under my active investigation. And I also discover new problems every now and then. So I guess in my practical experience in the environment of the Hong Kong research scene, this is a strategy that has worked, namely that I work on different directions. They are not absolutely unrelated, but on the other hand, they're quite distinct. So then when I expire on ideas for the moment, then I work in the other direction.
Sometimes in physics, there are physical equations that are waited to solve by physicists, but they find already there are solutions by the mathematicians. And I think it's sometimes when studying mathematics, it's like almost like you are discovering another world that we are no longer developing like structures, but we are looking for, and we see something that's already in maps, explained within itself. So I want to know, to your opinions, what makes mathematics such a structural object, a subject? I mean, so sometimes the thing is there are self-evident things in maths.
Yeah. So in a certain sense, you're asking why mathematics is so useful in certain studies in physics or perhaps in other subjects. So I take the point of view of a structuralist. So what mathematics means to me is anything that has a certain structure, including algebra, or numbers, shapes, patterns. My belief that if you want to have a meaningful science to study things that have a quantitative meaning or geometric meaning, then there should be an accompanying mathematical theory that comes with it. So for instance, you discover the group, right? The symmetry group. So you take a few objects and you shuffle them, and you can talk about probability and combinations and so on. So this is a finite group, the symmetry group. So first of all, there's a notion of a group, and then this notion of a group is a means to describe symmetry. But it can be used in other contexts, like in physics, in high energy physics. A lot of the descriptors are about symmetry in the system. And then of course, I was just talking about symmetry groups, but then you extend the theory, you get positive dimensional groups like Lie groups and so on. And it turns out that Lie groups were very useful machinery for the study of symmetry in physics, or the breaking of symmetry even. Right? Then the physics and mathematics interrelate with each other for a long time, and somehow they sort of bifurcated, but nowadays there's also a tendency of coming back. And when you try to describe the quantum world, there are structures in mathematics that have yet to be worked out. So this is, it's not, the flow is not unidirectional, it's in both directions. But as far as you go deeply into something, like even biology, so you try to describe evolution and so on. So you want to do predictions with the evolutions of DNA and so on. So then this is a new kind of mathematics that's being developed. Because it's a finite process, although very large, but it's still a finite process. And the kind of mathematics that was used to study physics might not be the right one to study biological systems. So the development of mathematics accompanies the development of other sciences. But on the other hand, for someone like me who does fundamental mathematics, pure mathematics, what I look for is something that has a meaning by itself, independent of the physical world, but which can be eventually applied to the physical world in different circumstances. Yeah.
Speaking of the program in our undergraduate studies, right, in the Hong Kong University in Hong Kong, so I think I observed this tendency, I'm not sure if that's true, that the programs are getting more applicable in the sense that we have fewer and fewer pure mathematics courses that are being offered. I can't help but wonder, how do we really promote pure mathematics to our undergraduate students? Because
I understand your question.
Okay,
so I guess it's a choice at the of each individual institution or each individual faculty.
That's true.
What to work on. And to give you an example, if you look at computational biology, so you actually need to know a lot of basic mathematics, like probability theory. Right? So it is a little short-sighted if you just look at the end products and not look at the basics, because it does not allow the student or the researcher to get into trying new methods. Right? So from my point of view, pure mathematics or the fundamentals like calculus, linear algebra, and probability theory, a lot of these things can actually be taught with a certain indication of their relation with the other subjects. There's no reason why the students should not be trained in these basic things in mathematics. And even numbers. It looks like numbers are something just like for fun. So you're just playing around with numbers, trying to see whether some functions can be solvable. But for instance, if you look at the cryptography, so to design some code, some scheme which is difficult to crack, one uses very deep mathematics. Like you can work on elliptic curves, for instance. So you never know the extent to which fundamental mathematics could move in to help you with solving problems. So nowadays one deals with data. So in data mining, then there's also already some new theory being developed to understand very big data by making use of topological ideas. The topology has to do with related to geometry. It talks about quantities which are invariant under deformation in geometry, and like homological constants. And these concepts have now been brought into use in the study of data, for instance. So you have to have some basic idea, for instance, like what is topology? If you don't know what topology is, you cannot even try to learn this subject. So I think it's advisable, and of course it's up to the individual institutions, depending on their focus, on their orientation, to introduce into the curriculum some basic things that would help the student grow.
Oh, speaking of curriculum, I noticed that there's this elite program, Science Masterclass, that you designed at Hong Kong U. Could you let us know more?
Well, the idea is to have some, I should start from the very beginning. Right? So at Hong Kong U, we had the students have the opportunity, I guess in other schools also, to have early exposure to research. So then they can take projects with the teachers. So this is one-on-one teaching. Well, it is quite rewarding even for the teacher. For the student, it gives him or her the opportunity to learn a subject that is not offered by the curriculum. So then we realize, of course, not just in mathematics, but also in other subjects, that the early exposure of a student to research and talking and doing a project with the professor is something that is rewarding and that would excite the students to speak. So this is the part of the reason why this was introduced. So it's something like, it's not exactly honors program. It's more than honors program because it emphasizes the contact with teachers. This is only our first year, so we're working on it. Yeah.
So the target students are all year one students? Or
yeah, they come in as year.
Oh, they come in as, okay.
Yeah.
Okay. I see, interesting. We do have something like that in our university. So Elena actually took my summer project last year. So we actually work on some research problem in mathematics.
Yeah, that's
well.
good. I mean,
Yeah.
this is,
Well,
the idea is that to be able to get exposure as early as possible, and depending on the subject, to get actually involved in the research process. But first of all, you have to have a broad basis of knowledge in order to do research. So one should not, of course, the active involvement in research, if you do labs, could be, of course, it's a very rewarding experience. But especially in the subjects which are more theoretical, learning a broad basis is as important. You can do research, but at what level? I mean, if you just do a high-level exercise, it's still rewarding, but if you learn more and you try to do something really novel, that's a different experience.
So, Professor Mo, you mentioned the importance of the broad base. So I have a question. So sometimes in our early postgraduate time, so sometimes we will feel that we are always not very prepared for doing research in mathematics. How do you think we could find the balance between learning and researching?
Well, when you get a problem, well, of course, you look for your own problem, or your supervisor gave you a problem and you work on it. Then it's very specific. You want to get it solved. Then whatever you have learned might contribute to your final resolution of the problem. So the broad basis is already there. So you have to have acquired a broad basis before being capable in solving difficult problems. So this is one point. Second is when you work on a problem, it's important when you read paper. So you try to understand paper. As this is especially true in pure mathematics. You have to find the punchline. So people write similar articles. Are they of the same importance? So then at that point, the advisor, mentor, or your peers who are knowledgeable in this is important too. So you have to be able to distinguish what is most important. Sometimes a lot is embedded. Well, it might be a very thick paper, but what is actually new might be very small. I think academics are not trained to say that this paper has only this much, the others are known. So you have to find a way to identify what's crucial, what's crucially new, and might be for a student this is a hard process. So then you need some help from people who are knowledgeable in it. So to summarize, what's important is that you have to optimize your capability. You have also to, first of all, you should have a broad basis to try to acquire along the way. And secondly, when you try to attack the problem, you should, from the very beginning, identify what is known, what's new in the nearest literature, and what is unknown. There's no point working on something that is just routine. So once you identify what is the hard part, then you feel then you work out a strategy to attack it.
According to my own experience, I think I'm an MPhil student, and I think it's a good way to think about this a toy problem, and through this problem you can learn some mathematics. And because when you are working some problems, it can not only motivate you to search for the literature, and find the answers, but also familiarize you with the knowledge you have learned. And I got similar questions. One was thinking of some mathematical problem, some unknown problem, or learning some new subject. Sometimes I got upset because I cannot find the answer, or I just find that subject tough for me, just like I was learning the category theory. So I'm wondering, did you have a similar experience, and how did you handle this?
Yeah, so when it appears difficult to learn something from the literature, how would I face it? Is that the question?
Yes,
yeah.
yes.
My personal belief is that if there is something deep in the subject, someone should be able to articulate it so that it's readable. If a subject is not very readable, either the reference you have chosen is not the proper one, or the experts have not agreed on things or have not done a good job. Then, of course, it depends on your experience. As you acquire more experience, you may try to translate what you can read from the literature in your own terms. But as an early researcher or as a young researcher, it might be difficult to do that. Then you need help, and that's the reason why one talks to experts. Nowadays, I think it's important, especially in mathematics, that you're on the right path. If you're on the wrong path, you should be going north and you're going south, and you're getting farther and farther away from the objective. So mathematics is a subject in which, as most of you are interested in mathematics, in which one has to understand things really very properly. It's worth spending some time identifying what is new or what is unknown, and before you put your whole efforts into trying to solve a problem. Because sometimes you waste time by trying to solve the wrong problem.
Might have observed we have more popular on doing like cross subjects, investigation of science, like you've mentioned. So we use the mathematical theory or
it's interdisciplinary.
Yeah, the mindset to deal with the machine learnings, and then sometimes for a student, his own subjects may be already causing him a lot of time or work to do it. How should they balance the time?
This is not an easy question to answer. Interdisciplinary studies in which mathematics plays an important part. It is of course very important that you know the subject very well. Right? So the assumption is that you know the subject and then you apply the machinery on it. But of course, if you are, on the other hand, a computer scientist or you're a statistician, you want to make use of the mathematical theory and apply it to other disciplines, then this is a different angle. What you were asking is about the curriculum, rather. So it has to be based on a wise choice of those people who are responsible for setting the curricula to work together. So I cannot answer your question specifically because it is formulated a little bit as in generalities, but I should say that tools are important, but the subject itself is, from the very beginning, more important than the tools. Right? So you have to learn a subject well, and the tools should be learned along the way in order to be applicable to the subject. So like you cannot just learn mathematics and apply it to biology, but you have to know biology in order to be a good computational biologist. So any attempt to do the opposite direction might produce you good papers for some time, but you cannot really make fundamental contributions from my point of view.
I'd like to ask a question about doing research. How do you handle setbacks? Like, what if, like we all have setbacks, right? Like if I got stuck when I want to solve this problem, I have no idea. And maybe after I submit a paper, I got a very tough review. So how do you handle the situations? For me, personally, I will just think about it after a cup of tea or after a walk. So may I know, Professor Mark,
how do I handle it?
Yeah.
Well, setbacks could be in different ways. For instance, you can maybe working on a problem and somebody else is working on it too. and you produce a paper, and then somebody else is producing a paper at the same time, or maybe even before you. So you get upset. Now, I think for mathematics, especially in pure mathematics, I'm familiar with the community, so I can say with more knowledge of this community than for others. It might be also true in other communities. Mathematicians are one community in some sense, and they tend to help each other. They tend to help each other. If you may know of the math genealogy project. You put in the name of a mathematician, you can trace his academic ancestors. I'm not aware of other subjects where you can do this. You would trace your name back to Gauss, for instance, something like this. So I think people do mathematics mostly out of interest from the very beginning. As a whole, I cannot talk about individuals, but as a whole, the math community wants the truth that they have found be known to the public. So when you meet setbacks, such as questions about priorities, then I think you should try to have a conversation with those who are also working on your own problem. And I wouldn't say that this was an example of a setback, but I can cite one example of my own. I was working on a problem, and many years later I see that I have a generalization which was interesting. And it happens at the same time somebody else was working on this generalization. And the person doesn't know me. He doesn't know me personally. He actually wrote to me. He told me that I have found this. And he asked me, but then he said that, but I think that you might have found it too. So the end result was very simple. He has found something, and I have found something from slightly different angles. And there are things that I have found that he missed, and vice versa. So we worked together and wrote the paper. And the paper in this way was better than each individual's contribution. And furthermore, it implies that there's further communication, and then there could be further work or the exchanges in mathematics. So this is an example in which this is not really a setback, but this is a kind of example where you may encounter when more than you yourself is working on the subject. And then taking the fact that it's a community and people like to work with others and then generate more knowledge, have more synergy of ideas. The advice would be to sort of optimize your contact points. And this should be an internet of people, and try to relate to others, and you can learn from him and he can learn from you. So I think this is a relevant example when it comes to priority conflicts. I seldom have any priority conflict in my career up to this point. So usually I don't work on problems that people have been very, well, of course I do work on hot problems, but I have different angles. So even if people might be working on the subject, results are quite different. So if you actually had examples like, let's see, the referee doesn't understand your proof. And first of all, you have to ask the very hard question whether it was your mistake. Right? If it was your mistake, you correct it, you do some, or you move on a slightly different direction, and try to see whether the true part of your own discovery can still come up, lead to a good paper, right? So then you have to be very objective, and you have to take the setback with an eye on the moving ahead. Right? Yeah, so this is what I would advise.
Speaking of collaborations, if there is someone, an expert doing some maybe subject you know nothing of, but they want you to join them because they think your knowledge to that field will be very good. So in that case, what will you do, or like what will happen?
Yeah. Okay. So if you are invited to join, of course, then you have to figure out whether this is likely to turn out to be a good collaboration. Right? It would be a very good collaboration if you have complementary knowledge. and then you can synergize your ideas. Usually, when you're invited to join a collaboration, if I am invited to join a collaboration, I would normally welcome having exchanges with the individuals. Whether it will eventually lead to joint work, that you have to, this has to depend on future development. Yeah. So I would take a proactive approach.
Do we have more questions from the audience, from our participants and scientists? Or if no, then I guess we can wrap up. And before we finish this section, I'd like to thank all the participants for joining us today. I hope you all have learned a lot from Professor Mok, as much as I do. To be the best, I think one must learn from the best, right? So that's the spirit of this masterclass. Now, may I invite Professor Mok to say a few words to us young scientists to encourage to pursue research.
Well, I speak from the point of view of pure mathematicians. So I think one should not, or the society as a whole, should not be just practically minded. Of course, the practical aspect is very important. But young people should, right from the very beginning of their education, develop their personal interests and their talents. And one thing I should mention is that sometimes you don't know your own talents. You must try to explore ways to, so to speak, discover your talents. Because you might know that you're good in certain things, you might be good in doing calculations, and therefore you think you should be a mathematician. But maybe that is not the real truth. The real truth is that you are somebody who's very analytical, and therefore you can also do other things. So I think we should grasp all opportunities to explore our own talents. And this you should do very early in your life. Doing in the undergraduate is a good place, but you can even try to do it as early as in high school. And teachers should also, as I mentioned, teachers should play a very important role in identifying the abilities of students also. I want to say that society as a whole might not understanding the evolution of knowledge in the world, and therefore they might not keep abreast with new developments. But you should trust also young people in their pursuit of new endeavors, and give them the chance to develop themselves, and they may break a new brave world.
Thank you very much, Professor Mok, for the very insightful words, and thank you for being with us today.